All right. So I think it's safe to say we've got a good group of people on here, Don. I'll just go ahead and introduce. So we're going to be talking about antenna placement and how it affects performance. So with that, Don, go ahead and kick it off, and we're looking forward to it.
Okay. Well, I've got 2 minutes early, but what the heck? If everybody's here, we can start. So we get a lot of questions about how to aim antennas, and it always has me wondering. So let's talk about this. The most important thing, of course, is to make my computer work. The most important thing is this, and you've seen this in my other presentations. This is the answer to everything wireless mic, right? What you have to do to make a wireless mic work is get your signal from the transmitter through the air into your antenna, down the coax, into the electronics. And when it reaches the receiver, the signal must be 20 dB above the noise floor, whatever that is, wherever you are. And when this happens, you have wireless. Your toes are kind of up to the edge of the cliff, but you're probably going to have a reliable performance. So if you can get this much level, you can stick a coat hanger in the back of your receiver. You can do everything wrong as long as you satisfy this requirement. You will be all right. Now, satisfying this requirement is an order of magnitude tougher now, or a couple orders, than it was 5 or 10 years ago. And we have to kind of do everything right to make that work. But you know, if you can, like I said, satisfy that requirement, then all you have to do is point your transmitting antenna towards your receiving antenna in a straight line, maintain line of sight, and you're good. Okay, conference over. I mean, that's it. For our purposes, with wireless mics and the frequencies we're using, radio waves move in straight lines. They do not bend around corners like sound does. So electromagnetic waves move entirely differently than sound waves do. So you have to maintain a straight line of sight. And that's it. That's how you aim your antenna. So there's, of course, a million variables in this, but that's what we're doing. So because we don't want to depend on a coat hanger stuck in the back of our receiver, we want to try to do everything that we can that aids in keeping that 20 dB minimum, or makes it better, 21, 25, 30, 40. I mean, you'd like to have even more reliability, so you have a less stressful performance. You know, wondering if you're if you're there babysitting the system, is this going to work all the way through? If we try to do everything that is beneficial and not give away anything because we didn't do it as good as we could have, that's what we want to do. So, like I said, aiming the transmitter at the receiving antennas. This is of primary importance. Like I said, it doesn't really go around corners. The way pickup goes around corners is the signal will begin to bounce off walls, and you got all those angles, and sooner or later, you know, like balls on a pool table bouncing off the cushions, it's going to go some other direction. But of course, we're losing an awful lot of energy. So that the level that you're trying to make that 20 dB out of is going down. So we want to keep our transmitter pointed at our antennas. We need to keep a distance away from our antennas. This pretty much happens automatically, but if you get very close to an antennas for the first couple of wavelengths, funny things happen. We don't need to go into that, but it takes a couple of wavelengths. So for us, we're going to call that 5 feet till the waveform kind of straightens out and behaves itself, and then does what it does for everything else. So you can get too close to an antenna, and these are kind of, the more gain your antenna has, the more distance you need. but this is just something to keep in mind. This is another thing to keep in mind. When you have a pile of antennas close together, they interfere with each other. And frankly, if you don't maintain at least 3.5 inches between your antennas, the antennas couple and become one bad antenna. So you see all that, all those whips coming off the back there, that's really behaving as one giant, very bad antenna. Because when the signal is passing through the antenna, it's creating a current, that's creating a magnetic field, and the magnetic field leaks over into the next antenna and causes a problem. It also makes for an array, like your line array speakers, your stack speakers, so you get the sound to go where you want it to go and no place else. When you have a bunch of antennas close together, and when I say close together, I'd like them to be 6 feet apart. If they're closer together than that, they begin to add up funny, and your pattern on the stage is likely to end up with hot spots and cold spots. So while you may have 20 dB at this spot, when you move to this spot, you might fall in a hole. You might have 30, you might fall in a hole. So we want to try to smooth out what happens. The other thing you want to do is you don't want to mount antennas too close to the wall. For our purposes, the ideal is usually to have it between 6 and 10 feet, 8 and 10 feet. You need to get the antenna over the top of people's heads so that line of sight is maintained. You know, people aren't blocking the antenna. And we'd like to have, most antennas need to be mounted at least a couple feet off the wall. You can kind of see the difference. If you mount it close to the wall, you get all these funny detunings of the antenna. And so you want to try to mount it a little bit away from the wall. And you need to keep your antenna away from metal. Trusses are generally not a good place to mount your antennas. In this particular case, CP beams can be mounted to truss because they have a back plate. They have a shield on the back side of the antenna. So it really doesn't care what's behind it because it can't see it. But regular paddles don't have that. And so they need to be mounted above, you know, you need to move them off the metal. These are a little close. Guess it was the best they could do that day. And again, if we can maintain that 20, you can do everything wrong. But making that even higher would be better. So the question I get a lot is, how far will my antennas reach? And the answer is they'll reach for forever. It depends on a whole bunch of other things, because it doesn't matter how far your antenna reaches if you can't maintain that 20 dB. So as your antenna goes more and more through the air, it loses power. And there's some other things in the system. So what you want to do is take a look at this. And we have a way, this is a great tool. This is our performance calculator. It's on every page of our website. Just click on that button and it takes you to this page where you can plug in some things and try it. So if you ask me how far will my diversity fin antenna go, I'm going to tell you it depends on how far away the cables are that are connecting it, what cables you're using, what microphone you're using. There's a whole bunch of factors that line up. It's not just distance, really, because if there was no interference, you'd be picking up wireless mics in China. But there is interference. There's that noise floor on the bottom that's pushing up against your dynamic range. So you simply just fill in these drop-down boxes. You don't have to get out any measuring equipment. There's no big bunch of math you have to do. This pretty well takes care of it. And if you get a green light, when you've selected all these things and pick through them, that means you have more than 20 dB. So you can see, change your coax length. Does it work at 25? Okay. Does it work at 50? Okay. Does it work at 75? Okay. Does it work at 100? Maybe not. Okay. Then I got to change cables or get closer. But you can put a bunch of variables in this and see what options you have. Because obviously, you'd like it to be a whole lot better. If you start with your antenna to distro distance of 25 feet, for example, like it's on the screen here, well, that's fine. And even if you don't intend to be 150 feet away, if you put that value in, you're going to see how much more stable your system is. If you're still getting a green light, that means with the 25, you're probably getting a whole lot better than 20. But anyway, this is an easy tool. We don't collect any information. I don't need your email address or your shoe size. Just go to the website and you can do this to your heart's content. So once we know, that we're going to get there, how do we aim our antennas? Well, the first thing you have to do is decide what it is exactly you're doing. Are you trying to cover a large area? Do I need to cover an entire room? Do I need to cover a football field? Do I have, or am I only looking at people on a stage? Are some of those people going to jump off a stage and run to the back of the hall? So the first thing before you're picking an antenna and you're focusing it is you have to understand what it is you're trying to do, because your different antennas will be better solutions than other antennas. So usually it comes to a choice of directional and omnidirectional. And when we say directional and omni, usually when we're talking about antennas for wireless mics, we're only considering the horizontal coverage. Most of the time, we're not looking to get somebody on top of a 10-story roof and on the front door in front of the building at the same time. If you're doing the Royal Albert Hall with 4 decks, well, that's a different story, but that doesn't happen very much. So usually we're only considered with the horizontal coverage. What goes up and what goes down, we really don't care very much about. So omnis tend to get used outdoors, and directional antennas tend to get used indoors. There are advantages and disadvantages to both, but a directional antenna, generally speaking, picks up less noise floor because it's only seeing it in one direction, where an Omni, because it's seeing in 360 degrees, is picking up noise in every direction. In this case, the way the antenna is in the back of the hall, it's pointed towards the stage, and I'm really only picking up RF in that direction. So it really doesn't matter what's behind me. I can't see it with the antenna, so the antenna is discriminating against that. So generally, you can pick between these two. I mean, if you're trying to do an outdoor event, for example, and you need to, your equipment is mounted in the center at the mixing position, and you've got to get the merry-go-round in one corner and the food booths in the opposite corner, you got to get all of that. And you can put your antenna in the middle. That's why you would use an Omni. In this case, a directional antenna is only going to pick up the east side of the field, and I'm not going to pick up the west side of the field very well at all. So basically, what the directional antenna just cuts the power of the Omni in half and puts it both to one side. So you're getting 2 times coverage on one side and 0 coverage on the other. It actually couples a little better than that because it's not a whole 180 degrees. So you get a little more than double the distance. So you need to be able to look at patterns, polar patterns. Everybody supplies this with their antennas. And pretty much, again, all we're concerned with is the horizontal, the x-axis, unless you've got somebody up in the air at the same time, and I mean way up in the air. So just imagine that when you look at a polar pattern, they're almost always arranged like this, so that it assumes you're looking straight up or straight north. And that's the center. So if you had a rifle and you were aiming straight ahead, that's what the polar pattern picks, and then you can see where the coverage is for any particular antenna. You can see as you get further and further to the side, as I get more to the 3 o'clock and the 9 o'clock positions, in this particular case, you can see that the power drops off. And in this case, it's scaled in 3 dB increments, or in other words, half power. So this particular antenna, where the curve falls to the outside and crosses that first line, that means it's only half as powerful there as it is directly in front. So you can see your coverage changes a little bit. So if you're right on the edge of that 20 dB dynamic range that we talked about in the first slide, like I said, you got to burn that one into your mind, because that's the question you always have to answer. So you can see directly, even with this, so this would be a typical paddle type antenna, usually have about 120 degrees of horizontal dispersion, but it is going to be stronger directly in front of it. And as you widen out, it's going to be a little bit less. So usually 3 dB is not a problem. That's pretty well figured into that 20. We're allowing for that because we know that's going to happen. But if you're right on the edge, do understand that you are getting a little less power. You know, this is all very similar to how you would use a microphone and mic somebody, right? If you point the microphone directly at the singer's mouth, you're going to pick them up with a lot of a signal. If they're off to the side of your microphone and not being picked up, yeah, you'll get them, but you won't get as clear a path to the microphone, so you won't be getting as much energy. So the same exact thing happens with antennas. Now, luckily for us, paddle antennas, like I said, they're almost all 120 degrees or pretty close to that. That's typically what depth perception is for humans, is 120 degrees. So really, when you're putting your antenna up, if you're going to put your antenna up on the back of the wall, you know, stand with your head against the wall and look forward. That's what you're going to pick up, you know, without turning your head. If you have to turn your head, that's what you're not going to pick up very well. So fortunately, that's kind of an easy way for us to figure out what's going on without actually getting out protractors and tape measures and all that good stuff. You pretty much can just look. And again, how far that's going to work is really how far it's going to work and be strong. And we go back to the performance calculator. So this is, I used an example here. This would be like our CP beam, a more narrow pattern, a 60-degree pattern, because it was way too big to try to get on a slide. So you can see where the hot spots are. And then you can also see, if you look kind of, you know, to the left down at the bottom, even if you're way off axis, if you're very close to the antenna, it's still going to pick you up. So again, this behaves pretty much just like a microphone does. You know, it's if you get close to it, you get a stronger signal. You get farther away, you get a weaker signal. If you're in the pattern, you get a stronger signal. And if you're outside the pattern, you get a weak signal. So, you know, we're trying, it's not that the antenna won't pick you up if you're not directly in the pattern. It's that your signal won't be as strong. And so if directly in front of the pattern, you are at that 20, if you're over here on the side, you're dropping some levels. So you can see here, we drop down, you know, 5 dB, 10 dB off to the side. It's still picking you up, but that 20 has dropped down by 10. So if you're 40 to begin with, you can afford a 10 dB loss, and you are picking up other stuff. So just understand that pattern is not fixed. It's not like walls. You know, it's not sealing you in. It's just the smart place to aim your antenna. So antennas generally almost all of them end up about like this, more or less. Your whip antennas, your omnidirectional antennas in the horizontal are 360 degrees. We actually have a new antenna, our Diversity Omni, is the only antenna that I know of that's actually a sphere. So it actually has spherical pickup. Regular quote unquote Omni antennas are more like a donut. It's more like you dropped a donut down over that whip. It doesn't pick up above and below. So that's a very good thing. One of the characteristics of our diversity Omni is it doesn't matter which way you point it at all. You can bend it any way you want. It's all the same because it picks up as a sphere. So paddles are generally about 120 degrees, like I said, which is about what your peripheral vision is. Helical antennas cut that in half typically. There are some that go down to 45 degrees. They're usually 60 or 70, something like that. So you kind of have these patterns that you're going to lay out over your floor plan to kind of see where your antenna is in the direct field. So where do we put our antenna? Well, a lot of people end up putting it in the back, which is perfectly fine. You're going to see the pattern, and you can see that as you move up towards the stage a little bit, you are covering everything in that room, right? That would be the red. And these would scale up, but they scale up, you know, if I scale it up, it's weaker out there. So you won't get as strong, but you can put it straight in the back of the room, or some people, you know, mount it. Maybe there's an overhang, you know, for the balcony, and they move it a little closer to the stage. Of course, getting your antenna closer to the transmitters means you get a stronger signal. That means you're gonna raise up on that dynamic range, that 20 that we're trying to hit. You'll benefit there because the noise probably really isn't going to change. Or if you put it, you know, way up closer, you know, if you have a soffit or something and you can get it way up on the stage, this is going to pick up your stage, which is what you want. But this also can be some benefit to you because it's not going to pick up anything that happens in your audience very much. And we have a new problem in audiences that have 5G cell phones that are T-Mobile 5G cell phones. They're creating interference. So the difference between having your antenna on the back wall and having your antenna on a soffit above your stage is you're going to have stronger signal because you're closer, and you're going to have less interference because you're not considering other things, your audience. Now, of course, you know, if you had an X-ray machine on stage or something, well, then that would be a different problem. But I have yet to been to a show that had a X-ray machine solo in the middle of it. So, but I don't know. I lead a sheltered life. Maybe you're into that. So you can see this is going to expand up, and even in the back, it is going to cover your corners in the back, but they're going to be weaker. So depending on whether that's a good thing or a bad thing for you could be the difference between that's where you mount your antenna and some other way. Now, if you need to absolutely pick up everything in a rectangular room with a diversity fin or with any paddle antenna, your best choice would be in a corner, because you are going to cover 100% of that room, right? When you put a 120 degree angle going out in a 90 degree room, you cover everything. You don't have to worry about what spills out the walls, probably, because the walls are going to block some stuff. So we'll just more or less consider that that's gone. So that would be a way to do it. And you can see, you know, it's going to spread out. It's going to cover that entire room. So if you have a play or something where you have an actor that has to enter from the rear of the theater, the rear of the room, this is a better choice. But it's going to pick up more noise in your audience. So we're always trading off things. Like I said, we got to remember what our job is, what we have to do. If I have to pick up somebody walking through the back theater door, then that's what I have to do. And I have to deal with whatever comes because of that. You can also mount antennas successfully in the wings of your stage. If primarily what you're trying to cover is only the stage and not the rest of the theater, you can see where this is going to cover. So we're still picking up part of the audience. You know, if our guy jumps off the stage and walks halfway down the center aisle, he's still directly in the pattern. He's still in line of sight. But you can see we're not picking up all the audience, so that might be a benefit, just depending on what you're doing. I want to point something out. If you're using two paddles, for example, and some people, of course, they have to be spread apart. They need to be at least 6 feet apart. Some people like to spread them very wide. And so you do get the benefit of, you know, less mutual coupling. Although once you get past 6 feet, there's not very much left. You're down to 1% or 2% or less. But it's still, you know, antennas 100 feet apart, couple even less. But what's happening, so if you're pointing these two antennas at the stage, some people think, or in a big room, they think, well, I'm spreading out the coverage. And the answer to that is yes, you are. However, it's only where they overlap in the middle that you actually have good diversity coverage. So that's a trade-off that you may decide to make. You may say, but I need to get, you know, this could be a huge room. This could be a football field or something where you have a really big distance you have to cover. You may be willing to take that chance, you know, or you could use a bunch of antennas. That's a whole different way to do it. That's more complicated and more expensive. But just be aware that if you spread your antennas, that your diversity coverage, and again, the antennas don't stop just in that overlap in the middle. They do cover. You still get some diversity coverage, but it's not even. And do you need that? I don't know. It just depends. But you need to be aware of this when you're planning how to lay out your antennas. If you're using mics and ears at the same time, and we are seeing a huge uptick in interest in in-ear monitors, especially the last couple of years since we started seeing a lot of streaming shows, right? So it's much easier for the sound mixer to get a super high quality mix. The less sound he has to deal with on the stage because the sound's going to overlap and bleed into all the microphones. So not having 4 or 6 or 20 wedge monitors up on stage certainly makes the sound mixer's job a whole lot easier. But you can't mount them like this. They definitely have to be separated. Now, I don't care where the electronics are. What we have to keep separated is the antennas, right? Because you have one antenna that's transmitting and one antenna that's receiving. So when they're close together, you're sort of screaming in the other one's ear, which is creating more noise, which is coming up against that 20 that we're trying to hit. Because we can't turn up the power on our microphones. There's a limit that the FCC gives us. And they give us that limit because if we had super high power microphones, we'd be bleeding all over somebody else's system. I just worked with a group last week that had just put in a whole new system, put in the DFIN and the distros and all that stuff. And then they started picking up the church from across the street. So they had to go make friends and do their channel assignments. So they weren't blocking each other. But this is, so you can't point a transmitting antenna at a receiving antenna, right? Because you're going to get interference that's very similar to, you're probably very familiar with this one, feedback. You don't want to point your microphone at your speaker. The same kind of thing happens. You've got one side transmitting, in this case your speaker, one side receiving, in this case your microphone, and bad things happen. So when possible, what you want to do is, the top example, you can see the transmitting antenna from the in-ear monitors is behind the receiving antenna. And even though that antenna is mostly dead on the back side, if they're very close, it's still screaming in its ear. So the better way to do it is to have the transmitting antenna in front of the wireless microphone receiving antennas a little bit closer to the stage, right? Because we're not, that transmitting antenna isn't really bothering what's coming back from the other side into the receiving antenna, right? We just don't want it to go into that antenna directly. So if you're mounting your in-ear monitor antenna and your wireless microphone receiving antenna on the same wall, it will benefit you to get the in-ear monitor antenna a little bit closer to your performers, even if it's a foot or two. That's a benefit. You're going to pick up, again, you're going to pick up a little bit towards that 20 dB dynamic range that we're trying to maintain. So if you're using mics and ears together, you basically have two solutions that are the best. Yeah, in this case, my wireless microphone receiving antenna is in the back of the room pointed at the stage, and my in-ear monitor transmitting antenna is in the wing, so it's 90 degrees to the receiving antenna, right? Or they can both go on the same wall. That's okay too. You know, that could be just as good because you're getting closer. I mean, there's trade-offs. You can't guarantee that one's better than another, but this is a very acceptable solution as well. What you can't do is this. You don't want to put one in one wing and the other in the opposite wing, and they're pointed towards each other. Right now now it's just like pointing your microphone back at your speaker. You're going to get feedback. You're going to get extra noise in the system. So this is the one we want to avoid. And of course, they can both be on the back wall, right? They're both going in the same direction, so they're not really pointed into each other. So this is an acceptable solution as well. And we got to use both things at the same time. So, I mean, so we're pointing our antenna at the transmitters. That's easy. Okay, so what happens when we have odd-shaped rooms? So here's an L, right? This happens. If I put my antenna on the back wall, if I'm going to assume that my stage or my primary interest is at 9 o'clock over there, I'm going to point my antenna towards my primary interest, and that's fine. But coverage down at 6 o'clock in that room, because it tapers off, remember the radio waves go in straight lines. So we're going to have weak coverage down in that corner. That could be a good thing, because I want weak coverage every place I don't have a transmitter. I don't want antennas to pick up stuff that I don't intend for them to pick up, right? So this may be a good thing. You may not need to cover that corner, but there may be something on the other wall that you do need to cover, and this would work. Or you can use a second antenna. In this case, I'm showing it with an Omni pattern. Like if you used our diversity Omni, you could put it in that room, and then you would slightly turn up the angle on your principal antenna. You do need to manage overlap. So it's never going to be perfect, and you're permitted enough overlap until you have a problem, but you're giving multiple signals out of time back to your receiver when that happens. And so that you're making it a little harder for your receiver to work. So when you use multiple antennas and you zone like this, or even if you just use 2x1 combiners to put this together, you probably are going to want to pad down that second antenna that's just covering, the room that's making the L out of your room. Or you could do it this way. See, if you put it back in this corner, you got 120 degree coverage. You are actually going to cover both directions of this L. But, that it just depends what it is you're trying to pick up. That's back to that defining your job. We have to know what it is you're trying to cover and what it is that you're trying not to cover. So kind of with those tips in mind, you look at the pattern of your antenna. Like I said, you got 360 for whips, you got 120 for paddles, LPDAs, shark fins. I'll call it what you want. You take that pattern and lay it out over your room to see where you cover and where you don't cover. When they get to be really big, then we'll talk about zoning systems. If you have, enormous buildings or multiple rooms or something. But if you're just in one room, one continuous room, you're simply going to take the pattern of your antenna, point it at your transmitters, direct line of sight above people's heads, and that's pretty much how you focus your antenna. So with that, I see we have some questions up there. And Adam, can you help me out?
Yeah, absolutely. That was great, Don. Thank you so much. Let's start with this one. So Andrew asks, can you talk about what materials might interfere with the transmission of RF energy, like humans, LED walls, and e-glass?
Well, okay. So what blocks radio waves? The short answer is metal and I should say ferrous metal and water. So yes, that's why we put the antenna above people's heads. If you're using a single receiver and you have it mounted on a desk or your mixing console and you're at 3.5 feet in the air, if you have people stand up in front of you, or maybe even at head height, they're blocking your signal. One person probably isn't going to wipe you out. If you try to go through a dozen people or 100 people, it's going to wipe you out. So obviously metal, that's pretty self-explanatory. That doesn't work. E-glass is a metallized covering that they put on windows to block ultraviolet. And it's only in newer windows. It's generally pretty easy to spot because it has a slightly gray thing to it. But then you're stuck with other, common construction materials. Sheetrock, concrete, brick. Okay, so sheetrock, might block 10 or maybe 20% of your signal. A lot of that is going to be based on the humidity where you are, because that sheetrock is going to hold water. So, this is going to be tougher in Georgia in the middle of summer than it is in Arizona in the middle of summer, because it's going to be dry and desert like there, and it's going to be humid in the south. And when it's humid, it's going to hold more water, so it's going to be a little bit more. Bricks, another thing that holds water. Concrete really holds water, so concrete's usually worse than bricks, which are usually worse than sheetrock. However, with sheetrock, if you're in a building that has metal studs and they are on 16-inch centers, so for a radio wave to pass through an opening, the frequencies we're going to use, UHF, 470 to 608 in the US, and other places are slightly different. We're going to call that wave roughly 2 feet wide. So if you have 2-foot studs, it'll pass through that. Just think of it as a solid piece of wood. You got to pass it, horizontally and vertically. So if you think of chain link fence, yeah, it's not going to hold water. Water will go right through it, but radio waves won't. The links, the squares would, if they were 2-foot squares, then that wall would be reasonably invisible to a radio wave. But it's got to be that big. So you do have to test for that. It's cutting down your signal. So again, if you're starting off and you've got 40 dB of signal, and your wall doesn't block 20 dB of signal, then it's going to work. You'll pick up through a wall. If it doesn't, if you're only starting with 30 dB of signal and you drop 20 in the wall, you've only got 10 left. You're probably not going to have a good day on the other side. So you do have to be aware of that.
Excellent. So we've got some more questions coming in. You'll have to bear with us. We're going to try to get to as many as we can in the time that we have. The next one is, how much signal to noise is too much? Many manufacturers say not to have your transmitter too close to the receiver. What's the likelihood of damaging the receiver with the transmitter being too close?
Well, I couldn't say damaging. That probably depends on exactly on your radio. Some things might be worse than others. So again, we're not talking about our dynamic range, but what we're talking about is our signal strength, right? So if you're again, you could get really close to an antenna if you have a really, really, really weak transmitter. They're fixed. You can't, if I was building one, I could make it, extremely weak. But what you're worried about is your voltage at that point. That's usually not a consideration unless you're going to be right next to an antenna. So when you're setting up your system, right? So we got everything set up. We got our antenna, we got our receivers, everything's wired up, and we're testing out the system. Turn your transmitters on and look at the signal strength, on the meter on your receiver. And if it's at 100%, then if you walk right next to an antenna, you'll be over that 100%. You'll overmodulate the receiver. You'd have to way overmodulate it probably to destroy it, to actually harm it. But it's going to go crazy, and you're going to get horrific distortion. The radio's going to drop out because the signal will be so messed up because it's so strong. So, it's like audio mixing console. You plug a line level signal into something that expects a mic level signal, all hell breaks loose. That is what happens here. So usually that's another reason to put your antenna 6 or 8 feet up in the air, 10 feet in the air, because even if you stand underneath it, you're holding your microphone, you're at least, 3 or 4 feet away from it, unless you're holding it up in the air, if you're trying to do this. But, that can happen if your antenna's mounted on a table and you're only 3.5 feet up in the air, and somebody walks over and leans over to talk to the sound man, and they get their transmitter right next to that antenna or something. That's probably not going to be good. It's going to overload the front end, and it's going to drop out, and it may make horrific noise in your system depending on what you've got.
Got it. Next one, Dawn. Is it all right to place the antennas behind a wood panel right behind the stage, also right under the LED screen?
Well, okay. So let's talk about the wood. Again, it's back to how dry the wood is. You are going to lose some signal. So when I talk about that 20 dB that you have to have, I expect you to be getting 30 or 40. A nice clean system. I don't want to make this sound all doom and gloom. You have to maintain 20. So if you lose a few dB to the wood, that's going to be fine in that case. It's just if you're if you're in a particularly RF noisy environment, that's the side of this that's sort of out of your control, right? So that's all the junk. That's where your LED screen comes in, right? Your LED lighting, the power supplies are little radio transmitters. Anything with a computer chip is a little radio transmitter. Anything with an electric motor that's spinning is a little radio transmitter. And then obviously any other radio you have is a little radio transmitter. So all those things are raising your noise floor. So when you raise your noise floor enough, it doesn't matter what thing, whether it was your LED wall that did it or other things, it's happened. And that's when you go off the air. So LED walls, the good news is they're a whole lot better than they used to be. The bad news is they still create interference. And sometimes the only thing you can do is mark off spots on your stage. Don't stand here because what you have won't work there. It'll work someplace else. Sometimes you can do that with specialty antennas, like our spotlight antenna can be used. A very limited coverage antenna could be used for IEM transmission. So, we can make your monitors work fine when you're downstage standing right in front of your microphone that you're going to sing into. But then when somebody else is singing and you decide to walk back and get friendly with the video wall, it's not going to work.
Awesome.
Video walls are a problem, and unfortunately, they broadcast interference on the same frequencies we're trying to use for our wireless mic. So there's a limit that you're going to hit. Hopefully it's workable for you. You may need to buy better radios. You may need to change your antennas. There are limits, and when you hit the limits, usually the next step is a bunch more money, to help solve it.
That's always the answer, right, Don?
It's always money, right?
We have a question about the spotlight that you just spoke of. So you spoke of LPDA overlap diversity. I have 2 of the RF venue spotlight antennas. Does the same overlap managing technique apply even though they are hemispherical? What would be your plan to deploy?
I'm sorry. So you're worrying about them overlapping for diversity coverage? As long as they're not 50 feet apart. So I'm assuming if you're going to use a pair of spotlights on a stage, you're mainly considering picking up information on that stage. As long as they're not 50 feet apart, at more than 50 feet apart, much more than 50 feet apart, you would stop having diversity coverage extended past those 250 feet apart antennas, right? So that would be a really big stage. It's more, when I was talking about that, it's more to do with if you're have your paddle antennas at front of house and they're split very far apart. That's mainly where you have to think about, am I really getting diversity coverage? And I should say, you don't have to have diversity to work. Diversity is a scheme that keeps you on the air. It actually damages your audio quality a little bit. So if you're in a noiseless situation, which never happens, but if you're in a near noiseless situation, you don't need diversity. But it's there to keep you on the air, right? It's better to be on the air with not perfect signal than to be off the air and have perfect signal that nobody hears, right? So that's why we want to worry about that.
Great. Whittling down the list here. This one should be easy. How high above audience heads should the antenna be placed?
Just a little bit. I mean, a foot or two. If you put it 20 feet above the people's heads, well, you've got a really tall room. There's no particular benefit in that, and then you have to aim the antenna down. Again, if you think about it, pretty much everybody's very familiar with how microphones work. If that were a microphone and you were trying to pick up a person, standing 20 or 30 feet in front of you, the closer that is to a straight level line, the shorter the distance is. And the shorter the distance is, that you get all the benefits of, you're going to get stronger energy. So it's not critical. But without knowing anything else, without making any measurements, what I typically want to do is I want to be above the audience head height. So if you have a convention of basketball players, it's a little higher, I guess. You want to be above people's head heights, and you don't want to be above the center line of the room, right? If you've got a 60-foot ceiling, you don't want to be all the way up at the top. They're sort of minor points. Above head height is because you're blocking line of sight. And if you block line of sight, that's a problem. Other than that, it's pretty flexible. Then it's mostly just distance. You want to keep it short. So it's not critical. You don't have to worry about it too much. But like I said, if I'm walking in, I haven't seen anything, I want to be above head height and no higher than the center line of the room height.
Awesome. So here's a good one. You touched on this very well in the middle of the presentation. We outfitted a room with diversity fin and the CP beam antenna for IEM. We placed the diversity fin in the stage right corner and the IEM antenna in the stage left. Should we move the IEM antenna to sit next to the diversity fin using the 6-foot spacing rule?
So I like you to keep them 6 feet apart. If you keep them more than that, it's not a problem. It's not a huge benefit. I'm more concerned about if moving them into the corner, if you have, I forget what the term is for it, but if you have a little short wall, coming into your stage and you're behind that in a corner, you're going to block some line of sight. So as long as you've taken that into consideration, in other words, you'll be fine across your stage, but if you need somebody to jump out 2 or 3 or 10 rows, you will be blocking that a little bit. So if that's important to you, then I would move them closer together. There's no particular, I wasn't saying that they need to be close together. They just need to be, if it's unobstructed walls, they can be on the same wall. That's all. They can be spread a little farther apart. It's not going to make a whole lot of difference till we start talking about really big distances. If we're talking about 100 feet apart, then we got to deal with that. But if we're talking the difference between 6 feet apart and 10 or 20 feet apart, 30 feet apart, doesn't really make any difference as long as you're considering your line of sight. You haven't blocked your line of sight at all.
Great. I think we've got some time for a couple more here. Is there a way to improve coverage for a large area for IEMs using 2 antennas?
Yes. You can simply take the output of your combiner, you can run it into a 2x1 splitter, and then you can run each of those to a separate antenna. Now you do lose 3 dB of power when you do that because you're sending half the signal to one antenna and half the signal to the other antenna. We rarely run into a situation where we run out of power, available power, when we're using IEM. So if I was in the middle of 2 football fields and I was trying to get the north or the, what is that in your screen? That's the west field and the east field. If I was trying to get those 2 and I had antennas going, but if we're not in a crazy situation like that, if you're just trying to cover like 2 spots in that L-shaped room, that would be a reason to do it. 2 different rooms, that would be a reason to do it. But no, you can do that. It just, or you just need to extend the pattern coverage. So you put 2 60s together, you got 120 coverage.
Great. And Don, this was last question, I promise, which kind of you segued a little bit into there. How do you know what output power you should set IEM transmitters to, and what length of cable would you recommend boosting it from standard to high?
Well, the goal is to have the least amount of power that works. That's an important qualification, that works. So the answer is different if I'm trying to hit somebody 300 feet away versus if I'm trying to hit somebody 50 feet away. I don't need as much power. You also have to remember that when you're using a circular polarized antenna, which you should be for your ears, you don't want to use a paddle or a whip. They're not good choices. They don't fail, but they're not good choices. A good choice is a circular polarized antenna like our CP beam. That's the other ones, that's the one you see on the sidelines of the football field, the plexiglass one with the curly Q on it. Plexiglass is a little fragile. So anyway, so now I forgot where I was going with that.
Lower power is better, I think.
Lower power, higher power. So again, if too much power creates difficulties for other things. So the stronger your power is, the more interference you're getting. So if you're only using 1 or 2 monitors, your power can be higher than if you're using 24. The same thing with if you're using wireless mics at the same time. So we have to consider all the radios together. So when you're using 8 mics and 8 ears, that's 16 radios. It doesn't matter which they are. You have 16 radios interfering with each other. And the stronger the power is from each of those radios, the more they interfere with each other. So again, back to as long as we can maintain that 20, you can do that. You don't have to worry about it. It's just what happens is even though you might make a measurement and you're getting 40, that's at the spot you make your measurement. If somebody steps over 3 feet and gets close to a big honking metal piece of stage set, or they drop their hand down to the bottom of the wireless mic and cover the antenna, or you've got a belt pack and the guy turns so now his body is blocking line of sight, you'll lose. So that number's not fixed. That's why we want it to be as high as possible, because, and even where you stand on the stage, you're gonna have higher spots and lower spots. It's inevitable. So all those things factor together. There's not just a single answer, but the lowest power you can run on is the best. So crank your system up, put everything on, turn it all on, and if it works, okay, now turn the power down. And if it works, okay, turn the power down again. If it works, then, leave it on the lowest one. And I should say, they don't all have to be the same. You could have some that are on higher power than others because that guy's going to go farther away, or there's some reason for that to happen. That's okay. They don't have to match. They just have to work. So whatever works, works. And we're good with that.
Awesome, Don. Well, I think that's all we have time for today. If anyone would like to give us some follow-up questions, you can just email me directly at adam@rfnu.com. I'll be happy to help. A lot of people ask for the recording for this session. It will be available. Again, just email me directly. I send them on demand once it's ready. So I'll try to send out another email as well to everyone with the recording in case you weren't able to make it today. So again, thank you for your time and your support of RFNU and all your questions, keeping us on our toes over here. So thanks again, Don. You're always awesome as usual. So we hope
to see everybody. Appreciate you taking the time to tune in.